Hello everyone, so we are back again. Now, in this class, we'll be describing the Navier-Stokes equation in plasma, how they look from for plasma that involves the charged particles, unlike the normal ordinary fluid where which are not charged, like say flow of water or flow of wind. So they are usually described by this Navier-Stokes equation, and how that changes, what are the extra terms that appear in case of plasma, because it is conducting in nature and it can respond to electric and magnetic field. So we will see that. And what we are doing in the last class, that we are dealing with the propositions of this two-T non-equilibrium model, and in the energy equation, what are the terms that goes into the electron energy equation and the terms that appears in the heavy species energy conservation equation. So we come to the conservation equations, which are essentially the Navier-Stokes equation for plasma. So these are the thing, that plasma is basically emerged from the plasma devices in the form of a jet. You can assume that it is a cylindrical jet, and which is basically dissipating, and it time comes when it just disappears. Okay, so it looks like a jet when it comes out, and the jet is usually having a cylindrical symmetry. So always it is more convenient to describe the systems in cylindrical coordinate. It is natural. So what we do, we assume a theta symmetry and describe the system in r, theta and z. Okay. So these are the coordinate systems. So one is radial, one is azimuthal, and one is axial. So you know that whatever equations we just derived in our fluid model, these are essentially nothing but that. You see here, so this one is what? This is the your time varying part, actually del rho Vr by del T. Okay. This is what? This is the convective part. So the plasma is moving as a whole, then this term appears, the convection term, and rho is the mass density. Then you see that we had discussed a lot about this grad p term in the momentum equation, right? So there, this is nothing but grad p term coming from there, and this one is involving one gradient in velocity and a coefficient mu. So this mu is nothing but viscosity. Okay, so this is basically the viscous stress term. When the one layer is trying to move over the other layer, then viscous force comes into action, and this term is appearing because of that. And then there is one term sigma r. This is very interesting one. This one is appearing because of the Lorentz force, and we'll see in detail how not only Lorentz force, there are some other force as well. They are again related to viscous stress, and I will give you a detailed expression of this thing. Apart from the your electromagnetic body force term, they involve the viscous stress term and one centrifugal term as well, because of the coordinate system that we are using. So that term also appears. Now the thing is that this term together we will call as a source term. Okay, so this source term, this sigma r, basically I have written here in detail. Whatever the terms that includes mu, they are all related to viscous stress. And then the term, this is called the centrifugal term, and this one FBR, it is the your J cross B force term. Whenever there is a current that is passing through the plasma, that current will produce a magnetic field of its own. then J will interact with B and J cross B will be the force that will be appearing as a body force into the plasma. So, what we have, this source term in the radial momentum equation includes the viscous stress term, a centrifugal term and a J cross B body force term. So, this one ABR. Similarly, in azimuthal direction, you can write the equation. They are again very similar to each other, and this term again your GADP term, this is the unsteady term, and this is the convective term, this is the diffusive term, and you are having a source term. So, this source term now in case of plasma again having some your viscous stress term. So, these are the things, and these are all involving this your viscosity coefficient of viscosity, this mu, and again this is the your centrifugal term, and this is the your body force term. What is the this thing? Now, when you are considering the this axial momentum conservation equation, now you know that J is in a direction, whatever it is having, it can have some arbitrary direction, not necessarily to be radial or axial or in theta direction. So, depending on the kind of orientation, it can have component in all directions. So, this sigma r, this is sigma z actually, may or may not include this magnetic force term, your J cross B body force term, because if you orient J in Z direction, and then it will naturally give a B in theta direction, and J cross B will be in radial direction, but J cross B will have no component in J direction or B direction. So, J cross B component in it will be directly radial in that case, and it will not have any Z component there. But in when you are doing a numerical simulation, so this term will be J will be arbitrarily oriented depending on the kind of situation, and you can have a component here as well. So, what you are getting here, that this sigma z, again it is involving all the viscous stress terms, this source term, and that is how it should look, this source term. Now, if you note that how the momentum equation is appearing as a whole, you will see that it is having a convective term, a unsteady term, and then a pressure gradient term and a diffusive term, and then it is combined with a source term. So, each of them are having that. This is again you see that convective, this is time varying, this is the pressure gradient, and this is the diffusive term. Same for axial as well. You see all the terms are present over here. So, as far as the momentum conservation is equation is concerned, you see that they are having a general nature of behavior, which is having a convective term, a unsteady term, a pressure gradient term, a diffusive term, and a source term. Now, we come to the energy conservation equation. So, I already explained you how this equation should look, and I have exactly written the same equation, just copied and pasted over here. So, this H is enthalpy. So, this is the convective term. So, convective energy transfer. So, this is rho V into H, and as usual this divergence is there, and this is the conductive heat transfer. So, divergence of K grad T, this is the J dot grad D term, and this is the Joule heating term, and this is the radiation loss term. One interesting thing I would like to tell you, that here also you are having a convective term, this is a diffusive term, and you see that there is no pressure gradient term of course, but there is a source term which includes this Joule heating and energy loss due to radiation. Now, when we are solving that current continuity equation, that if you write that in terms of potential, then you can get this equation where phi is the electric potential. Now you have to apply proper boundary condition together with this set of equation to solve this problem. So I will show you the actual simulation study exercise where how we implement those kind of things in practical problems, in practical systems. I will explain those things. Now this set of equations, what you are getting now, you can consider they are the Navier-Stokes equation for conducting fluid like plasma. So they describe the plasma fluid, motion of plasma as a fluid similar to the Navier-Stokes equation, which earlier people used to use for this flow of fluid like say liquid or gas kind of thing. Now this in this slide we write the conservation equations. As I already indicated you that all the conservation equations, when they are reaching the steady state, you know that this time varying component will disappear. Then what you are getting? You are getting a convective term, a diffusive term, a pressure gradient term, and a source term. Okay. So, and as I told you that we are interested in the steady state equations most of the time, but of course if you want to understand the transient behavior of some plasma system, in that case you have to consider the your time varying part as well. But as I told you, the time scales range over a very wide range, and getting a very realistic transient behavior is a bit difficult, but it is not impossible. You can do that using supercomputers, and then also you have to restrict yourself within some range, and you probably cannot handle the full range starting from nanosecond to second at present, but it may be possible in future. So if we consider only the steady state systems, then what the equations for this mass conservation equation, axial momentum conservation equation, radial momentum conservation equation, azimuthal momentum conservation equation, then potential equation, then heavy particle energy conservation equations, and electron energy conservation equations. So you are seeing how many there? This is 1, 2, 3, 4, 5, 6, 7. 7 equations are there, and the very interesting fact is that all of them, all these equations which describe the plasma as a fluid, they can be written in this form. This divergence of rho v phi equal to divergence of gamma phi grad phi plus s phi. What is this? This is the convective term is equal to diffusive term plus source term. And what are the different values for different equations? I have just listed in this table. You just put phi equal to 1. You get back your mass conservation equation. You know, when you are putting that your phi equal to say Vz, then you just put phi equal to Vz over here, and in place of gamma, what is that? You replace gamma by mu, and then what you get? This S phi as this thing, and you see that here we have put for Vz Jr b theta. Similarly, we will put that Jz b theta for Vr, and then we have this thing azimuthal component. We need not to handle this two terms over here, and then we can write this source term as like this. Okay, this is some simplification is there, but in general this can appear if it is having some arbitrary direction of j. But when the j is your axial, or you say that it is some sort of 2D distribution and there is a theta symmetry, then this term may not appear over here. Now what you see that we have only one equation. That is very interesting and that is very important as well. That makes our life much simpler, because you see that Here we can constitute the mathematical framework to solve only one equation. This is the equation, and if we are able to design that framework and implement to solve equations one after the another, then only one equation basically you need to solve, and you are just changing the parameters like phi, gamma phi and s phi, but the framework remains the same. So this reduces the coding load, or this numerical load significantly. And there is some advanced modeling where somebody uses the chemical non-equilibrium as well. What is it? I just let me tell you that that ionization equations, what it was saying in a plasma, that any Ni by N0 is something, right? Now this any Ni and N0, you are considering something equilibrium condition. Now suppose there is chemical non-equilibrium, that in the surrounding zone some reactions are happening which are producing some electrons or some ions, and because of the gradient those ions or electrons are diffusing into the zone where you are trying to solve your equation. Now ionization equation doesn't know what are happenings in the surrounding and which has to be accounted. So when you account the fluxes because of the chemical reactions that are happening in the surrounding, and you modify your this ionization equation to get including the source terms which are originating due to the reactions happening in the surrounding, then the your this thing what you call the number density conservation equation gets bit modified, and that gets this look. So this nk dot is a rate equation, and this rate was earlier defined by the ionization equation Ni by N0. Now what is happening, that this S1 is the steady state one. Now what is happening actually, this is getting modified by the fluxes from the outside, and this G, J are the diffusive fluxes. You see, there are some grad of log T terms, and then gradient of density terms, gradient of pressure terms. Now they are contributing to the flux, additional flux. So if you include that and solve the number density conservation equation, then that is some modeling including the chemical non-equilibrium in the system. So this is a bit advanced, and without considering that also you get a pretty good result which are very close to what you observe experimentally, and I will show them how close they are. And that even if you are including this chemical non-equilibrium, sometimes the deviations are there, and there are many other reasons which come into the play, you need to take into consideration. I'll discuss all those things as the cases appear. Okay. Now, when you are going to solve this set of equations, now you have already seen that there are a large number of terms in the source term, and when you are going to handle a practical system, you really need to include all these terms. You cannot avoid any of them, and they have to be properly accounted. You see that in the electron energy term, what we have used here, this J square by sigma. This is the J square by sigma term. This is generating the energy. Then this is J dot grad D term that has appeared in this equation like this, and you see that this sigma x is the collisional exchange term. Okay, so this collisional exchange, electrons are losing the energy, minus sigma x, and the same energy has been added to the heavy species energy equation here. Okay, so these two things you should consider, that is one is losing the energy amount of sigma x, and the same amount is getting added to the heavy species equation by plus sigma x. Then you see that Joule-Leading term, J square by sigma, as I already told in the proposition, that we are including that only in the electron energy equation. Okay, but not that is included in the heavy species energy equation. So heavy species, how they are getting the energy? Through the collisional exchange only. Electrons are gaining energy from Joule-Leading as well as losing energy through collision, and this one 4 pi UR here, This is very special to plasma because of high temperature. This is the radiation loss term. Again, this is negative, you see. So, this radiation loss, this collisional exchange loss, this J dot GAD T term, and this J square by sigma term, all these terms are basically new compared to the ordinary fluid. In ordinary fluid, none of them actually appear because they are low temperature, so this radiation loss is not there. They are only a single fluid, so this collisional exchange is not there. Then this one, you consider this Joule heating because they are not conducting, so it will not appear there. So these terms making the plasma a unique fluid, and these terms actually a primary this energy terms that influence the behavior of the plasma. Okay, so we now understand that how the plasma fluid equation differ from an ordinary fluid by this this magnetic body force term, J cross B terms, and then it is by your in the energy equation it is through Joule heating term, J dot GAD T term, radiation loss term, and collisional exchange term. So that is how the plasma fluid differs from an ordinary fluid. Now, how to solve these equations? We know the set of equations that we are having. They are mass conservation equation, momentum conservation equation, species conservation equation, current conservation equation, and energy conservation equation. Now you know. What are the things that we require to solve the equations? It is only the numerical technique or something else we need? We go back to that. You know that if you really want to solve the equations, then what are the things that you require to know? Without that, you can never proceed. These are the things. Say, rho. What is this? This is the mass density, a thermodynamic property of the fluid that you are using. Now, when you are going to calculate this gamma, the diffusion coefficient term, this gamma phi, you see that you need to know the viscosity once, and then next time you need to know your thermal conductivity. For the potential equation, you need to know the electrical conductivity. So these are the transport properties which you require to know. Even though you know the general form of the equations, you will never be able to complete this equation without knowing the coefficients which are formed out of the transport properties of the plasma, like viscosity, like your electrical conductivity, like thermal conductivity, and all these things. And there are many diffusion coefficients which are appearing if you are going to go for this advanced modeling. So what you need basically to solve those equations, even though you may having beautiful equations, you are not in a position to solve those equations, absolutely not in a position, because you are not having any information about the transport properties. Actually, these are the properties which govern what behavior the plasma will show. So knowing the thermodynamic and transport properties are the basic requisite, basic requirement for solving the set of equations that governs the plasma system. So they are so much important to know. Without knowing those things, you will never be able to solve any of these equations. So first requirement in this thing, we do have the set of equations, but we are not in a position unless we know the properties. How the property depends? It depends on what kind of system you are considering and at what temperature they are. From that, actually, we can estimate the properties. So initially, how do you know that thing? What do? We make a guess that this plasma is now sitting at this temperature, and these are the species, possible species in this system. Then what do? We go to the property code, and depending on the species temperature and species density that we have made an initial guess, we calculate the thermodynamic and transport properties. So once it is calculated, we know that all the transport coefficients like your viscosity, thermal conductivity, electrical conductivity, all these things are available. Now to calculate those, what we need? We need to know the density and species temperature. Initially what we are doing, we are taking that as a guess, and these collision cross sections and collision integrals are very much required, as I have told you in the beginning classes how to calculate the thermodynamic and transport properties. So you use those collision integrals and use the guess value. Now for the first time when you are starting this simulation, you go to the property code and then you get calculate the transport and thermodynamic properties. You feed back to the fluid dynamic code. So now you have basically two codes. One is solving the fluid dynamic equations and one is giving you the thermodynamic and transport properties. They are independent codes. So but they depend on each other's input. So to run the property code, you need some density and species temperature that is given by the fluid dynamic code. It takes those values from there, then it starts working independently. Then it calculates the thermodynamic property and transport properties, and it gives back to the fluid dynamic code. Once it knows the coefficient values, it starts solving those set of equations, and then it comes out with a new solution for temperature and the species density. So now you have a set of species density and species temperature which are no more depending on your guess. It has been returned by the fluid dynamic code. The first time you guessed, second time it is returned by the fluid dynamic code. Now this density and species again fed back to that property code. Property code calculates the revised thermodynamic and transport properties and feeds back to the fluid dynamic code. So now whatever fluid dynamic code is getting, it is gradually trying to reach to the actual values. Then it recalculate the species density and species temperature based on the solution of this fluid dynamic code, and then they feed back to the property code. So this cycle actually goes on and on and on and on. Then what you see that the change in the number density and change in the species temperature distribution over the zone where you are solving, their change becoming less and less and less as you move on more and more iteration. So a time comes when the change in the density or temperature distribution over the zone becomes really insignificant as you move for further iterations. So when such situation comes, we say that the simulation has converged. So in such situation, whatever the distribution of species and the distribution of temperature that you are having over the simulation zone, they are the steady state solution for the kind of system that you are handling. So this is basically the way how one finds the solution of the fluid dynamic equations in plasma and get the distribution of pressure, temperature, species inside the zone. And they are the agents which basically facilitate the process that you are handling, because you are going to use the plasma for some process. Definitely without the unless that is there is no attraction of the plasma. So what are the agents in the plasma that are doing those jobs? They are the species and the species temperature. So density of species will matter, species temperature will matter, kind of species will matter, and what are the set of species that is present there, what kind of reaction that they can do. So all these things matter, and those informations will be in your hand once you are solving this set of equations with the help of the property code. So you must understand that solving the equation is one thing that is important, but finding the transport and thermodynamic properties is another thing which is very, very much important to know. Without that, you cannot do this thing. So both of them, I can say, equally important. Rather, fluid dynamic codes are available there, and solving those set of equations is rather easier because of people are doing this for long time, and it has now achieved a standard framework for solving these equations. But when the property things comes, now you know that if you include equilibrium, if you include non-equilibrium, if you are using this chemical non-equilibrium, things change a lot actually. And then the moment the properties change, your transport properties or thermodynamic properties change, the solution changes. So fluid dynamic code is blindly relying on the property values that you are supplying. If the properties are wrong, then your simulation is wrong. So although fluid dynamic code can give you exact solution, very correct solution, but that solution will have no use if your property values are not correct. So, and there are many concerns about the property code, because now also you can improve the properties. There are scope of improving the properties. There are lots of scopes of improving the properties. So that is why property code is one of the area where people are still working, and they are trying to improve the values under specific conditions that are there. So in the next class we will be coming to the solution of the this fluid dynamic equations in plasma, and how to proceed and what are the results that we are getting. Okay, so this much now. Thank you. We will meet in the next class.